Welcome back, Method students. We're going to work through 9b and a few different examples in this video. So this is where we really start to look at the process of differentiation. And differentiation is still talking about, like the last video we looked at, we're still talking about rates of change or the gradient of a function, but now we're looking for the gradient of a function at a particular instant. So not the gradient between 2 points, but the gradient at one single point on the curve. Little bit of notation here. If your original rule is written as y, then the derivative will be written as dy dx. And if the original rule's in function notation like f of x, then the derivative is written as f dash of x. As we just said, instantaneous rates of change, so not average rates of change, but instantaneous rates of change, is found by differentiating the function and then substituting in the x value of the point where we want to find the gradient, okay? Because the derivative is really a rule for the gradient at any point. If we want to make that a specific point, we substitute in the specific x value that we want. Okay, this rule here, really important for polynomial functions, or really any functions in the form x to the power of a number. If your function's in the form x to the power of n, then the derivative f dash of x will equal nx to the power of n minus 1, which in words just means you multiply by the power and then subtract 1 from the power. And hopefully you're used to doing that a fair bit from your Year 11 methods, and these first few examples will just be a reminder of how that process works. So let's get stuck into example 1. We're told that y equals 3x to the power of 4 plus x squared over 4 minus 7. And we're being asked to find dy dx. Well, to do this, what we're really going to do is just differentiate term by term. And so the first one will be, well, multiply by the power and then subtract 1 from the power. So 3x to the power of 4 becomes 4 times 3x to the power of 3. You can see the power's gone down by 1. Then, same thing with the second term here. We're going to multiply by the power, which is 2. Then subtract 1 from the power, which gives us x to the power of 1. Now, minus 7, this is an interesting one. A lot of people will just learn that, well, if you differentiate a constant, it sort of disappears. And that's true. But one way you can think of about why it disappears is that this is really like having x to the power of 0. This is the number 7, the constant negative 7, is really like negative 7 times x to the power of 0. So you can see what would happen if we multiply by the power here. Well, we're just multiplying the term by 0, and therefore it's going to go away. Okay, so we don't get a final term. Okay, so the derivative of a constant is actually 0. Okay, so what's left to do here is just to tidy up these two terms. We've got 4 times 3, well, we know that's 12x cubed, and we've also got 2 times a quarter here, so we can simplify this into saying it's x over 2 or a half x. Okay, and obviously we don't normally write to the power of 1, so we can just drop that off. Okay, so there is our rule for dy dx. And so for part B, it says find the gradient when x equals 1. Well, what this is here is a rule for the gradient at any point, right? Any point on the curve, we can sub in whatever x number we want. If we want to now work out the gradient when x equals 1, well, we're just going to find, I'll write a different color, we're going to find dy dx when x equals 1. Right, we've already got the rule, so let's let x equal 1. And dy dx when x equals 1 becomes 12 times 1 cubed plus 1 over 2, which is really, well, 1 cubed is 1, so 12 plus a half. We could write that as 12 and a half, or we could write it as 25 on 2. So in other words, the gradient when x equals 1 of this particular function is 25 over 2. Okay, next question, find the values of x where the gradient is 0. Okay, so this is saying not that we're subbing in an x value because we're trying to find the x value, but we're actually substituting a value for the gradient. So gradient is 0 really means that we're going to let dy dx equal 0, okay? Because dy dx represents the gradient. Okay, so we go back to our rule, right? That's dy dx. We're going to let this equal 0. So therefore we get 12x cubed plus x on 2 equals 0. And our job is to try to solve that for x to get the value or the values where the gradient will be 0. Okay, little trick, you've got equal 0 on the right hand side, you've got it divided by 2 that maybe you don't like the look of. You could multiply everything in the equation by 2, and that'll give us, 24 x cubed plus x equals 0, if you prefer to deal with whole numbers. Strategy for solving this, well, we've got two terms. We actually have a common factor here of x. And we can now solve this by factorizing. We can actually solve this using the null factor law. So therefore, we're going to get x equals 0 or 24x squared plus 1 equals 0. Now you might be able to see what's going to happen here. 24x squared equals negative 1. X squared equals negative 1 over 24. But this last step, whoops, gone off the screen I think. This last step here isn't going to yield a result, because if we try to say x equals plus or minus the square root of negative 1 over 24, well, we know we can't take the square root of a negative number, so that's got no solution there, that's undefined. But we do have a point here when x equals 0, where the gradient will be equal to 0. So a couple of examples there of how we can use a gradient rule, right? So we found the rule for the gradient, which is, we found the rule for dy dx, which is the gradient at any point. In part B, we tried to find the gradient at a specific x value by substituting in a value for x. In part C, we kind of did that the other way around. We tried to find where the gradient's equal to 0 by substituting in dy dx equals 0 and then trying to solve for x. All right, moving on to next section here. Another similar example, but just a reminder as well of a rule that you might not have used for a little while, and that rule is that gradient equals tan theta. That can come up in lots of differentiation questions. I mean, anything to do with gradient can come up in differentiation questions. So this rule is where m is the gradient and theta is the angle that the straight line makes with the positive direction of the x-axis, which really just means, don't have a lot of room to draw a good sketch here, but if you had a line kind of going like that, positive direction of the x-axis is as you go to the right, so that would be theta there. Okay, example 2. If f of x equals x squared minus 3x, find the value of x such that the tangent to f makes an angle of 45 degrees with the positive direction of the x-axis. Okay, this stuff about a tangent to f, really, we know that tangents are associated with the gradient of a curve. So if we're thinking about gradient, even if we don't know exactly what we're going to have to end up doing in the question, let's just start by differentiating, because if we're talking about gradient, we're probably going to need the rule for gradient. So f dash of x is going to be worked out by taking f of x, multiplying each term by its power, and then subtracting 1 from the power. So x squared will become 2x to the power of 1. I'm just going to leave that 1 off. Minus 3x, well, that's really minus 3x to the power of 1. And so if I multiply by the power, I'm just multiplying by 1. So I'm still going to get minus 3. But when I subtract 1 from that power, I get x to the power of 0. And 3x to the power of 0 is really just 3. So my derivative function, f dash of x, is just 2x minus 3. Okay, now this is saying we want to find out the value of x where the tangent to f makes an angle of 45 degrees with the positive direction of the x-axis. Well, if I've got this rule here that says m equals tan theta, and I know that my angle is 45, well, I can actually work out what gradient this is talking about. If gradient equals tan theta, then for this question, gradient will equal tan 45. And if I know my triangles from circular functions, I don't need a calculator to work this out. I know that that's 45 degrees there, and so is that. So tan being opposite over adjacent, tan of 45 is just 1. Or 1 over 1. Okay, so what this question is asking me is actually to find the value of x such that the gradient is equal to 1. And if I know that, well, then I'm just going to go back to my rule and let the gradient equal 1. So let f dash of x, because f dash of x is what's representing the gradient, equal 1, and then I'll work out my value of x. So I'm going to get 2x minus 3 equals 1, which means 2x equals 4, which means x equals 2. Okay, so the value of x such that the tangent to f makes an angle of 45 degrees with the positive direction of the x-axis is x equals 2, and that's my final answer. Now, not necessary to draw a graph here, but just so we can picture what was going on. Okay, so this is like a, optional extra. All right, this original graph here, f of x, was a parabola, and by quick inspection you could see that it would have x-intercepts at 0 and 3. All right, it'll be a positive parabola, so it's going to look something, and I say something because this is not a good picture, but it's going to look something like this. Right, now, at some point, okay, if you imagine trying to work out, and like the way I'm holding my ruler here is just like all these different tangent lines, right, all these different instantaneous rates of change. What we were trying to find was what point would we get a tangent line that has a gradient of +1, right? And what we worked out, again, my picture's not very good because the gradient isn't quite looking the way it should, but we worked out that it was about here, right, roughly, when x equaled 2, where we get a tangent that has a gradient of +1. Or more specifically, as it was worded in the question, we get a tangent that would cross the x-axis at an angle of 45 degrees. All right, that was what the question was all about. Okay, so again, that picture wasn't necessary in terms of your working or in terms of getting marks for the question, but it's good to try to picture what was going on anytime you're answering one of these questions. And even if this picture is just in your head, that can be a really helpful thing to think about as you're working through an example like this. Okay, those couple of examples are a little bit long, so I might just cut this off and then I'll do the third example in a separate video. So we'll see you in the next one.